In this short tutorial, I'll show you how to sketch and identify rational functions having removable discontinuities. A removable discontinuity is a point on the graph that is undefined or does not fit the rest of the graph. The way you identify one is that if you find a restriction in the function that can be cancelled out, this will result in a hole leading to a removable discontinuity. Now, just keep in mind that we did this before with vertical asymptotes. We looked for restrictions and we made them to be vertical asymptotes. The difference here is that when you have a vertical asymptote, as you get closer and closer to that restriction, the output either becomes more negative or more positive infinitely, but never quite reaches the restriction. Whereas here, you don't get that effect. In case that's confusing to you, let's take a look at question 1. They want us to sketch the graph of the function f of x is equal to this rational function. Remember what a rational function is? It's when you have a polynomial divided by a polynomial, and that's the case here. And find the coordinates of all removable discontinuities. So they're asking for removable, not non-removable, which would assume it's vertical asymptotes. As you can see, at the bottom we have x plus 1, and at the top it's x squared minus 1. That's a difference of squares that can be factored as x minus 1, x plus 1 over x plus 1. As you can see, the restriction at the bottom, given that this is a fraction, this part, if you set it not equal to 0 and solve for x, you end up with x cannot equal to negative 1. So that's a restriction. The graph doesn't exist at x being negative 1. However, if I were to, at this point, cancel out these two factors, I don't have this problem anymore. I would have x minus 1 only. If you see a rational function do this, then you know that it is a removable discontinuity. Graphing f of x, where the function is x minus 1, you would end up with a straight line, obviously. This is a first degree equation. And if you take a look at the graph, you'll notice that there will be a hole at negative 1 and negative 2. Simply take the restriction, in our case x cannot be negative 1, and substitute that into x, and you'll end up with f at negative 1 is negative 2. So expect a hole at negative 1 and negative 2. Let's see if this effect occurs in question 2. Sketch the graph of f of x is equal to the following, and find the coordinates of all removable discontinuities. What we have here is a quadratic that can be factored. In fact, if you factor it correctly, you end up with x plus 3 and x minus 2. Two numbers that multiply to negative 6 and add to positive 1 are positive 3 and negative 2. Now, this factor at the bottom can cancel out with that, leaving you with 1 over x minus 2. Now, rewinding for a moment, if we have a rational function, then the bottom, the denominator, cannot equal to 0. Therefore, we would have an asymptote at x minus 2 cannot equal to 0, so that becomes x cannot equal to 2. You would have a vertical asymptote at x being 2. The reason why that's a vertical asymptote and this one isn't is because this factor would cancel out with the factor above. So this would be a removable discontinuity at x equal to negative 3. You would have a discontinuity there. Substituting negative 3 into this function, substituting that into there, we would end up with 1 over negative 3 minus 2, and that is 1 over, or negative 1 over 5. You would have a removable discontinuity at negative 3 and negative 1 over 5, and a vertical asymptote at x is equal to 2. A visual representation of this function is shown on your screen. And the reason why I'm not showing you how to sketch is because all it is knowing what 1 over x looks like and then using transformations to get your function the way you want it to be. So there you have it. That is how to sketch rational functions having removable discontinuities.